Hi everyone, welcome to meeting number 25 of the M2D2 series. Today's speaker is Marco Bertolini. Marco is a ML research scientist at Bayers in the group of Oko Clever. Marco's background is in theoretical physics, where he obtained his PhD from Duke University on the mathematical formulation of string theory. He started to tackle machine learning problems during his postdoc at the University of Tokyo. Currently at Bayer, he is developing machine learning models on histopathology images and developing GNN for small molecule property prediction and the explainability of both types of models on the different type of input. Thank you so much, Marco, for accepting our invitation to present today. And just before giving you the floor, I'll just say to everyone, today is the last talk of for the summer. We'll be taking a break and restarting in September or late August, depending. And we are collecting your opinion on how to improve the talk series when we start again. So please, if you have time, fill out the survey that I just shared in the chat. That'll be really appreciated and help us like serve you at the best we can. Thank you all in advance for filling the survey. Thank you again, Marco, for giving the presentation. And without further ado, the floor is yours.
Thank you so much. Thanks so much, Prudential, first of all, for the invitation to talk at this series of talks, of which also have been as spectators a few times, and they're really nice. But also, I promise I will also fill the survey because it's important giving feedback. And just like a quick, and also, yeah, thank you for the nice introduction. That was really nice. Also, feel free to anyone also to ask questions during the talk. Feel free to raise your hand. If I should be seeing your hand being raised, if I don't, also feel free to unmute yourself and just ask your question and stop me. If you're too shy, then I ask Prudential please to then moderate and stop me. So whichever you prefer, asking question during or after, there's absolutely no constraint on my side. So that being said, okay, today I want to talk about a work. You can find a preprint on ChemArchive. Is this ugly link? I can also post it in the chat later, so you can just click on it and it's easier to find. But also, if you Google the title, it's weird enough that you're gonna find the right page anyway. And it's a work done by me and with some help from colleagues within Bayer. And it's about explainability for property prediction models. So before we delve really into the details, let me start with some motivation, right? Why do we even want to develop a new explainability model for a method for such models? Here on the left, I hope you all can see my my virtual laser pointer. There are the two most common types of neural networks, right? For molecular property predictions. Very popular are SMILES-based networks. So the input is a SMILE string representing a molecule, or graph neural networks in which the molecules represented as a collection of nodes and edges. So it's embedded in some topological graphs. And both these models have been having quite a bit of success in predicting various properties with a high accuracy. Now, when we want to do explainability, what can we do with these models, right? I mean, typically explainability, what we do is that we compute with a given method. We associate to each input feature a number, right? And this number is supposed to at least correlate to the importance of the specific feature in the specific prediction. Now, the nature of these models is that, right, the input in this case is one feature is one character in the smile string, right? So that these methods will assign to each character that basically, except the parenthesis one, let's say, right, represent an atom, a specific number. And same for graph neural networks, right? I mean, in which then to each input node, which again represent an atoms, we associate a specific, the attribution method will compute a number, right? So the first challenges in these approaches is obvious, is that it's so-called an atomistic explanation, in which each atom is individually analyzed and it's assigned its explanation. So these methods basically by construction avoid explanation that involves more, if you want, global concepts. So maybe bigger structures, for example, rings, etc. At the same time, we know that chemists rather think in terms, I'm not a chemist at all, as you know, I'm a physicist, but you know, I'm told that, you know, chemists like to think in terms of bigger structures, right? I mean, subgroups or rings, and they don't think really in terms of individual components. Other challenges of these approaches is, for example, as we see in this example here, is often the lack of symmetry of explanations. This, especially for smile-based networks, is not surprising, because even though the molecule might have some symmetry, the fact that this is represented in a smile string, this automatically breaks the symmetry. So it's natural that the network, even if you perform the task pretty good, will not learn to encode the symmetry of the molecule, and this is reflected in explanations. This sometimes might confuse the chemist because he or she might say, well, the molecule has a you know, if you want mirror symmetry along the y-axis here, why is this contributing negative and the equivalent counterpart positively? Also, perhaps minor, but still another challenge is often the lack of stability. There are, for example, multiple smiles corresponding to the same molecules. These will have often different explanation, which is also not a very desired property. Finally, given that in both approaches we assign to each atoms a number, often these explanations tend to be quite cluttered. And then it's kind of confusing for a human really to extract the really important features, as you know, then it might be hard to understand really, for example, in this picture, what's actually contributing positively, since most of is actually all green. Okay, with this a little bit of introduction for the motivation to come up with a new or a different explainability, let me now introduce all the ingredients of the types of model to which our formalism applies. We focused also, because these are models which are really relevant and also in use in the company at Bayer, on models based on CDDD's descriptors. Perhaps not everybody's familiar with those, so let me quickly review what these are. These are, as I said, descriptors, which are continuous descriptor, which were introduced by Robin Winter, also a researcher in our team. And these are the bottleneck layer of an autoencoder, which is trained to reconstruct, if you want to translate between smiles and canonical smiles of a molecule. So if you want, these are continuous because it's bottleneck of an autoencoder, and you can use them as descriptors, right? I mean, instead of fingerprints, we can use CDDD's descriptors. So given a new model, we can just compute a new task. We can take the input models, we compute their CDDDs, and take these as input for the model that you want to train, right? So for some user model that is going to tell you some chemical property prediction. Once we have then this trained model, for example, as we see, we can compute, in the case of smile-based model, right? Because CDDD is the original, it's really a smile. Smile is attributions. So how do we compute these attributions smiles attribution internally. This is also a method we developed and is actually implemented internally. So for smiles, it's a little bit tricky, right? I mean, because all the gradient methods, which are nice in many domains, are a little bit tricky. They are technically, mathematically well defined if you just code them up and let them run, but it's a little bit tricky, right? I mean, because each character in the string is actually, if you want, a one-hot encoder representing the specific atom type. And so it doesn't really make sense applying, you know, a continuous gradient to such input. So we came up with a little trick in which we say, well, we sort of construct a discrete version of a derivative in which the attribution for a given spot in the string is given by taking the prediction as it is, and then subtracting the prediction that one gets by replacing the specific character in the string with all other possible characters, and then one takes an average to sort of not overweight a specific replacement. So this, if you want, is just an extension to discrete space of a continuous derivatives, and this is the model that we use it right now, and then later in the talk we will use to compare and benchmark our proposed new explainability. The key factor, yes, I see potential.
I have one small question on the previous slide. By doing this permutation between one character and all the possible ones to kind of get how this character contribute to the activity, sometimes you'll be breaking like the rules of chemistry and also making the smiles invalid. Have you kind of tried to restrict the option to the ones that don't break the rule of chemistry and also don't break the grammar of smile, and see if that impacts the attribution?
Yeah, actually, this is actually what we actually did, right? So it's not we replace any character, but at least we check that the smiles is valid. So at least that check is into place. Yeah, so because then we still need to input the smiles into the model. So in order to have something sensible, we at least check that. Yes.
Okay, perfect. Thank you.
Right. So now, okay, right. The other key component is a model which is called image to model, which is actually developed by Occo Clevert, which is the lead of our group. So the original scope of this model was actually a molecular depiction recognition, right? So given an image of a molecule, say in a patent, in a paper, or on the internet, the goal of the model was to recognize it and translate it to its canonical smiles. The way this was trained is actually not end-to-end, if you want, but given an image and the corresponding smiles, the network, the encoder, if you want, was trained to map the image to the CDDD descriptors of the corresponding smiles. Okay, so it was basically a minimization problem in CDDD space. And then if one is interested to actually take the smiles, one can use the decoder, if you want, the old one from really the CDDD autoencoder. And this is going to be the key component of this talk. Then before going there, the final piece of information to really build the whole model is just as a use case to really show some example, which kind of downstream models we're going to use. So this is a very simple downstream model in which is just two fully connected layers. So it's actually a multitask model with two property predictions, log D and log BCF. Today we will only look at actually log D, but just sort of for having, you know, one specific use case and not mix too many things at the same time. So it's a very simple model, and again, the structure is is very simple. Again, we have a smiles, we get the CDDD descriptors, which is a one vector of 512 dimensions. Those are our input to the models, which we can train. Exactly. So this is the concept then of the rest of the talk, right? I mean, this is what I just described. This is how the network is trained. So smiles in. So the encoder part is not fine-tuned or anything. This is basically just to compute the embedding, the fingerprints if you want, and only the orange part down here is trained. But as we saw, the image-to-model network and the CDDD encoder, they shared the same descriptor space. So the whole thing would work if we would just replace the CDDD encoder with the image-to-model encoder. And also, just to point out, and this network is not retrained. So this network is only trained with the, if you want, the original smiles-based encoder. But for the point of view of inference, if you want, we can just replace that encoder with images. And now we have a model that goes from images to prediction. And that we can also use to extract explanation now in pixel space. Okay, so are there any questions before we go a little bit more into, this is sort of the idea of the structures of all the models and what they are used for.
One small question. So even if you've trained the CDD model to output the same representation for the smile and the image, I'm sure that in reality there's some small discrepancy in the values, right? So how do you account for the fact that you never have a zero loss on such training?
Yeah, that's a very good point. It's a very good point because obviously you're correct, right? We expect, in some sense, for us, it's also a check, right? At the beginning of this project, would it even work, right? Exactly for the point that you mentioned. But we also experimentally saw that, yes, if we validate or if we test the model with this setting in comparison to this, the model performance decreased a bit, but not by too much. And so for us was also a sign of robustness of the whole setup. And later, we will also see that we can also compare the explanations to see that they correlate, that they are sensible. So basically, the answer to your question is we checked and we saw that the decrease in performance was very minimal. So then we went ahead with it.
Okay, I see. Thank you.
Okay, so exactly. So now that we have, we want to extract now explanation in pixel space, also using all the literature about explainability for CNN, which is much bigger than for other types of models. And in particular, we will see that we will use the fact that we have several representations at several points in the network. And before going then in the specific details of the of this model, I want to give a little bit of also overview, also why we had this idea by summarizing a couple of slides, sort of the theoretical framework that we also put out on arXiv in a preprint this year, that then led to kind of the use case that we talk for the rest of the talk. Since the idea is that there's a different role somehow, right? We have this embedding space, which is shared between two different models, and there's a downstream task, right? So this embedding space is an important role in the whole process, right? So in this work, we had, so the goal that we had in this work was actually developing an explainability framework for whole embedding. So not just for a single output for a single task, right? Some classification or some regression output, but really for a whole, if you want, embedding of any dimension, right? And our idea is actually very, very simple. And basically, and we will see this idea then in the specific case. But the idea was simply saying, okay, now we have an embedding, which is some number of dimensions, and we can take each of the embeddings components separately and treat them as if it was an output. And so we can basically, for each of the components of an embedding dimensions, we can compute the saliency maps as you with the strategy that you preferred, with just gradients, integrated gradients, activations, time gradients, whichever strategy you like. And now you have a plethora of explanation, right? One for each of dimensions. And then we said, okay, we just then to obtain one single saliency map, one single explanation for the whole embedding, we just aggregate them. The simple aggregation is to sum them, but other aggregations are possible. And in the paper, we explore a little bit the statistical meanings of different types of aggregations. So it's very simple. And now we have all of a sudden a way to visualize a whole embedding and not just a specific task. On the other hand, we also, given also the literature of recent years in which more and more papers point out that actually deep neural network learn and store high-level concept in deep layer. For example, you can think about TCAPs, for example. We said, well, let's not just restrict ourselves to go back to the input space with the gradients if you want, but let's actually have the freedom to compute these saliency or attribution if you want at any point in the network, right? This is a little bit of bookkeeping because you need to split the network in only forward and the one in forward and backward, but it's actually not that hard. So now that we have a way to visualize a whole embedding, and for example, here in this middle row, you see visualization of embeddings of some hidden embedding on some ResNet. And now we said, okay, of course, imagine we do some, for example, unsupervised learning. Of course, we would like to know not just why a certain predict, because there's no prediction, right? There's no downstream tag, but we still would like to know if the embedding captures the important features of the input. Then we came up with a way to measure this using attribution, using XAI, and we came up with a very simple measure, which we call the noise score. And basically, and the idea here is that okay, attribution then come from an informative representation, right? From a flower, from some image that means something to us, should actually be different in average than a representation that comes from noise, right? I mean, or for some that involves some randomness. And basically, we measure then somehow this informativeness of a representation by then taking the difference between meaningful and so attribution coming from a meaningful and noisy input. So here, for example, in the bottom row, you see same network, but with a noisy input, and we see that it looks much more uniform than the attribution coming from a meaningful input, in which so basically in this direction we increase the layer depth. So at the beginning, of course, is much more about geometry, and as we go deeper, it just focuses on some parts of the picture which doesn't happen in the noise counterpart. Now, it's very interesting then to analyze what happens statistically a little bit over a whole data set. And here, I don't want to go through the whole slide, but just focus on a specific plot in which we took as a method activation times gradients, and then we compared. So, right, I mean, here we have This is our ResNet 18. So here we can compute, sorry, I'm just going to go back 1 second, right? So since we can compute these attribution maps per layer, right? I mean, the embedding is fixed, but we can compute them for each layer given by P. And then we compared over a whole data set what happens. We plotted the noise score for a trained and an untrained network, for example. And we see that at the beginning, the two curves are basically the same. And this is very nice, right? I mean, so basically, this is the statement that basically the noise score cannot distinguish an untrained versus a trained network for saliency maps that are mapped back to the input. This is very nice because this is exactly one of the main statements of this by now famous paper by Adebayo, these sanity checks for saliency maps, in which they say, well, activation times gradient cannot distinguish, basically they claim is insensitive to parameters of the model, because basically they cannot distinguish whether a model is trained or not. And the motivation here, the reason is quite simple, because since we multiply the gradients by the activations, going all the way back to the input space, the multiplication by the activation, which in that case is the input itself, has such a big impact on the saliency maps that it doesn't matter what the gradients are in some sense. So it doesn't matter whether the network is trained or not. And so one would conclude from that paper that actually activation times gradient doesn't satisfy one of the sanity checks. We, however, said, okay, but let's actually look throughout the all networks. And we see that if we go deeper and deeper through the networks, actually the difference starts increasing, meaning that this effect is fading out, going in the middle of the network. And we say, well, if we actually consider the full picture of the whole network, then attribution times gradient becomes quite a sensible attribution strategy. Because here, I guess, the effect of the attributions get diluted and the gradients become much more important. And we see that then the noise score can quite well distinguish between the two. So basically, here the bottom line is that explanation for embeddings are important, and it's also important to look at the whole network and not just limiting ourselves to the input space. Now we can come back to image to model and see how all of this plays out in this case. So the first thing that we did is to check. This is also very nice to apply these techniques, because I mean, the inputs, you know, the input space of such models are very, in some sense, simple, right? If you compare to natural images, right? This is a molecule is pretty much black lines over a white background, right? I mean, so it's a very clear, it's a very specific distribution in pixel space. Let's put it this way. And so we looked at what actually, so we can just visualize the activation in the given layers and see what they are. And even though it's totally expected, but it was really nice to see that if we look at the very early convolutional layer, the filters are really either node detectors or really, for example, edge detectors. So for example, this is edges at a particular angles. This is our sort of horizontal edges. This is like the edges in the other diagonal, right? I mean, like the kind of filters that one writes by hand in machine learning 101, right? I mean, there it is, right? And the deeper we go into the network, we see that, I think there's a question.
Yes, sorry, hi. I have a question, a pretty simple question. When you're performing these saliency maps on these networks, do they truly come as neatly as you show in the slide, whereby sort of this heat map around a particular area of the molecule, or did you have to do some sort of cleaning to sort of zero down the region of interest?
You're talking about this slide, right?
Yes.
Okay, so this one is actually, so there's no cleaning. There's just a rescaling, because as we go down in the network, sort of there's some pooling, right? Basically, when when the square here becomes smaller, there's some pooling, means that actually the input is we need to sort of expand it, right? I mean, scale it up. So that's the only cleaning up, or if that's the only transformation we apply, but there's no thresholding or cleaning it up. It's just the network itself learns that the interesting stuff happens where the molecule is and not outside.
Okay, because I was just really taken aback by at least the edge detectors on how you can basically see how neat sort of the saliency is kind of focused only on the edges of the molecule.
Yeah, and here we don't even need to do the rescaling because no pooling happened yet. So it's really like what the filter basically is triggered by.
Okay, thank you.
Nice, and basically, yeah, and as I was saying, if we go deeper into the network, we see that the filters of the network start focusing on bigger and more global features, right? I mean, so in the middle, start picking up rings or somehow different kind of structures, right? And at the end, it really focuses on subparts of the molecules, right? So we go from really edge and node detector to ring and substructure detector. So basically, it will be an awesome dictionary to express our explanation with, right? Because these are really something that makes sense chemically, right? I mean, and so, and these are our activations, right? So basically, that's what we then wanted to implement exactly by then following the study that we saw before, right? So by looking at the whole model, now we have our encoder, image to mol, right? And lambda here is the specific downstream task. So we have for each of the layer, right? So P is a fixed layer, but we want to do for all of them. We can compute this horrible formula is just the precise way of writing gradients times activations. So basically activations are these, right? I mean, so these are our activation in the specific layer, and gradients are going to be the importance given to these features learned by the filters. And once and these are basically this A, P are these pictures here, right? I mean, so basically these, we go from very locally based explanations, again, mostly edges and nodes, to deeper and deeper and deeper to explanation that involves bigger substructures. Then we want to have a pictures, like a global pictures, like not having multiple explanation, but just one explanation that involves only one pictures that involves both local and global. And basically we just sum them. So we aggregate them by summing all of this, and we obtain our final explanation, which we call contextual, because according to the context, we have either global, local, or both. For example, if we look at some examples, in the first picture here, it's pretty obvious that we have the whole ring is considered as a whole here as a negative value, if you want, and then single atoms are also highlighted, which are deemed important for the prediction, relatively positively or negatively contributing to the prediction. Are there any questions here? Because basically this is our method, and now we turn into trying to analyze how this method might resolve or at least improve over the challenges that I talked in the very first slide.
Marco, there is a question by Yang in the chat. So basically, Yang is asking if you rotate the molecular image, would you expect the same region ring, for example, to be still active as well?
That's
So
an
basically,
awesome question
any...
because this is going to be my next slide.
Cool.
Okay, so that's awesome. Okay, so but this is something that that I mentioned at the beginning is symmetry, right? I mean that often attributions from smiles do not respect the symmetry. And now, as was just asked, right? I mean, there's lots of transformation and lots of symmetry that is present in pixel space, and we want to quantify to which degree our attribution are robust or are invariant with respect to given transformations. So let me try to explain how we're going to quantify that just by cherry picking some results, right? Which is always somehow working out. So this is a little bit the mathematics of it, but we can just look here at the picture, right? I mean, here's the idea. We start with a molecule and we apply a transformation. In this case, is a rotation by, I think, 30 degrees or something like that. Then we can compute the attributions, the explanation for both. And then we can rotate the attributions of the unrotated ones. And then we can compare. In other words, we can first transform and then explain, or we can first explain and then transform the explanations, and we can measure to which degree these coincides. And we measure this by the simple score, in which basically is taking these two, right? I mean, the first explain, then transform, that, and first transform and then explain, and taking the difference and then averaging over a set of molecules and then see which what do we get, right? Of course, a perfect symmetry will be we'll have a score of 0, so we want to have lower scores, right? This is 0 if and only if really A and T commute, right? I mean, so this diagram commuting will correspond to a score of 0. So let's look at something that I alluded at the beginning. So a symmetry, so we have molecules that are either symmetric or almost perfectly symmetric around basically the y-axis, right? So basically some scores of mirror symmetry. So we send the x coordinate to minus x, and we can compute the our contextual explanation and the smiles-based explanations, and we can compare. We compute the scores for each of those. And for example, here I also have written the specific score of this specific molecule. Here, everybody would agree that, you know, that the molecule is the explanation is perfectly symmetric, and it corresponds to a score of 0.13, right? I mean, of course, in pixel space, I mean, a little bit of a difference of intensity, and the borders are not very precise, so you'll never get really a 0, but, you know, so a score of 0.1 is already quite good. And here is over, I think if I remember correctly, at least 100 molecules. And we see that the smiles explanation have, in average, a much higher score than the contextual or the image to mol explanations. So we see that our interpretation is that the graphical depiction of a molecule breaks less the symmetry than the smiles strength. And this is also not surprising that the explanation coincides, because, I mean, image to mols was also trained with lots of augmentations. So the molecules during training was seen with all kinds of transformation, rotations, and flipping and all of that. So it's not very surprising, but it's nice that, you know, this challenge seems to be, if not resolved, quite, you know, improved by quite a bit. Then rotations. Here I didn't. I just wrote the problem that for smiles-based explanation, there's no rotation, right? I mean, so basically here I didn't plot the score. I just written and I just chose so some examples, but in average, also here we have pretty good symmetry. of the explanation with respect to rotation, for example, in this case. And here on the right, we have, for example, if you use RDKit, you have several ways to depict your molecule, right? You can choose the thickness of the bonds, you can choose the way to represent the rings, whether to have written all the carbon and hydrogen atoms and so on and so forth, right? I mean, and also by using different graphical depictions, we also have quite a bit of symmetry. Here, for example, I combine several. So here is both, we can combine several transformations, both different strategies for graphical depictions and big rotations, almost by flipping and all of that. And we see a good mapping of the explanations as well. Right. So far, we have seen basically, okay, how these explanations are computed. And basically, we check there's some robustness or some self-consistency, right? I mean, that they are robust with respect to transformations. They are robust with respect to flipping and graphical depictions. But often in chemistry, it's very hard to know the actual ground truth of a task, right? I mean, in natural images, it's much easier to know if an explanation makes sense because we all know the correct label, right? We know what's a cat and what's a dog, right? In chemistry, even chemists struggle to know why a specific molecule has a high prediction and as a high property for a specific task. That's why also they rely a lot on machine learning model, but it's also hard then to evaluate the correctness of explanations, right? So since we don't have a good, at least I don't have a good grasp of what makes a good or a high log D for molecules, we train just kind of as a simple task, a model that is supposed to recognize whether a benzene ring is present in the smile or in the molecule, just to have a ground truth and then see whether our explanations correlate well with the ground truth. So the model reaches easily, very soon, 100% accuracy on any test set. And again, we perform the same game in which we measure how good our explanations are by taking the difference between our explanation and the ground truth, basically in a graphical form, right? And here are some examples on the right. And here are the results. So basically, we see that image to mole is on par with the smile explanation. Both models perform quite good. And first of all, much better than random, which is this red line. And it was funny to notice that even with an untrained, which kind of relates to the question that was asked before, even an untrained downstream task using the trained image to mole performs much better than random, just because the filters and the attributions are so much more focused on the molecules that by chance every once in a while they get some benzene ring, but the trained version, of course, performs much better. And I think this is actually my last slide. The last thing I wanted to share today is we expect, right? So now we have these two explanation methods, and the claim of our work is not so much use images, don't use smiles, right? I mean, I think for the point is that often one explanation misses something. So having a possibility of looking at a couple or a few explanations obtained through different methods might complement each other and might give a bigger pictures, right? I mean, but anyway, we would expect a correlation between the explanations, right? I mean, they might differ in some molecule, they might differ in symmetry consideration and all of that, but in the big picture, we would expect a correlation between the explanation coming from different methods for the same prediction. So this is what we measured here. Again, very simple. So this is some examples. So we generate explanations with both methods, and then again we compare them by again taking the difference and then average over a certain data set, and we found again the score average of 0.12, right? I mean, which as we saw before, that usually 0.1 is a pretty already good agreement between such heat maps. So we concluded that they sort of agree what's important, and then and our idea would be that, you know, for example, a chemist, you know, that runs a prediction on some property prediction model would have a disposal, right? He or she could click, okay, please explain this prediction, because I mean, maybe I'm not expecting it, and would have then, for example, both explanations, right? I mean, and right, I mean, in some cases maybe they're completely equivalent, right? I mean, but maybe here, I would say that here, okay, it's clear from both models that this ring, it's very important, but here it's very, maybe it's hard really to understand, okay, what's really positive, what's negative. And so maybe in this case, I will be much more obvious looking at this picture. It could be other cases that is the other way around. So it's more the idea of complementing explanation and giving the chemist additional vocabulary to understanding in an easier way explanation than really just, you know, replacing. So yes, thank you so much for your attention and for your questions already, but feel free to ask more questions or clarifications or suggestions.
Perfect. Thank you so much, Michael, for the great presentation. Very interesting work. Any question from the audience? Don't be shy to open your mic and ask a question. If not, I can start with one. So one thing that you said at the beginning, not at the beginning, but like when we were starting to show the result, is the image to model has been trained with a lot of augmentations, and those include like some rotations and everything. And I was wondering, because like the SMILE version of a molecule have multiple, we can also augment and do some randomness. I was wondering if when you were training the SMILE to model, you were mapping to all the different rotation kind of permutation that you can have on the SMILE side as well, or only you're just mapping to the canonical SMILE all the time. And if you think that doing so is something that can actually also improve the maybe the attribution for the SMILE molecule as well.
Yeah, that's a good point. I'm just trying to go back to the maybe, yeah, here maybe. Probably yes. It's true that there's some augmentation here to some degree, in the sense that the model is trained with basically the given molecule is presented in very different equivalent SMILEs that they all match to then the canonical SMILEs. But you know, the point that, you know, from my point of view, right? I mean, this model was presented where I wasn't even part of Bayer at that time. So for me, is sort of a black box I received, and the development at that time was not so much on let's have nice embeddings that have specific properties with respect to maybe explainability. So, you know, the main focus was having very informative. That would, you know, so basically, are we performing much better in some, if you want, side task or downstream models? So that was the main objective, right? So so that wasn't the goal at the time, and this might be part of the reason why maybe the explanation might look sometimes a little bit counterintuitive. The problem is, so of course one can say, okay, let's retrain a new CDDD that sort of alleviates these issues. The problem is that they actually, as they worked quite well, and there are already models in production that are based on those, right? I mean, so it's also not just we want to explain future model, but we want to explain models that are already used and they're not going to be changed, right? So so in some sense, your point is very valid, and probably one can try to train more interpretable, maybe with some constraints or with some other tricks, a more intuitive CDDD space, but that still wouldn't help us with, you know, really from the practical point of view, with models that are already in production with the old ones, which they work so well that it's hard then to replace them. But on the theoretical level, yes, I completely agree. It would be nice to think about it.
Okay, perfect. Thank you. One question from Dominic in the chat. Can the model be used for GNN since it mostly rely on activation while constraint yourself to images?
GNNs, I mean, okay, so I guess the answer, it depends. Definitely the general idea of extracting information from different layers can be applied to any network. So it has nothing to do with images. There were two reasons why we did it with images. First of all, we had all the ingredients, right? The CNN image to model was there, right? I mean, and was exactly mapping to the same space as the other one. So in some sense was opportunity. Apology. The other reason is that GNN are still, right? I mean, for CNN is very easy to understand if it's just a pure CNN with the most pooling, right? I mean, I always have a way, as we discussed before, to map it back to the original space without and still map it, right? I mean, to the original, right? I need to do some rescaling to match it back to the original space, and then I know that this comes from this specific field of view, right? I mean, so I can still map an internal and hidden embedding to the original space. For CNN is a little tricky, right? I mean, also because even if I don't use pooling, I still have, even for hidden embeddings, I still have nodes, right? I mean, so I'm still gonna have, I don't have this pooling effect that I can get to global things. I get to global things by updating the node embedding through message passing, so that the node embedding of layer 5 has seen much more of the network, but then it's hard to then map it back to the individual component, right? So bottom line, yes, we can do it, but I think then the interpretation would be a little bit harder. But other than that, yes, and perhaps it would be actually a very nice use case to also explore.
Cool. Thank you. Yeah, thank you so much, Marco, for the answering of the question and for the great
Sorry,
presentation again.
I opened the chat and I saw a question from Yen that I think, yeah, asking if one wants the higher log D, is it possible to redesign the molecules? That's a very good point. And it's something that honestly we are a little bit thinking about. At this point, I can say, right, I mean, also not being a chemist, but I mean, I think XAI can guide you there a little bit because, you know, you have, let's just take one simple example, and I apologize if I'm going over time, but sorry, I'm just trying to get to the first usable example, which may be this one, right? Okay, let's suppose we have like a molecule like the one in the middle, right? I mean, and we know that, so the explanation can be interpreted in the fact that the green areas are contributing positively to the log D, and so I don't know if you can see my mouse, but and the pink or areas are contributing negatively, right? So one could imagine, oh, sorry, maybe let's go here, which is easier, right? The idea could be, okay, if we remove this, right? If we remove something that is purple, technically log D should go up because we remove something that brought the prediction down, right? So probably if we do that, probably you will get the molecule with a higher log D. That almost sure, right? The question that often when chemists try to optimize a molecule, there's a whole lots of constraints that they need to take into account at the same time. So maybe this functional group is very critical for other properties, right? I mean, but if you just care about log D to have a higher log D, I would say, you know, we can remove what contributes negatively and we should get the same molecule with a higher log D, or we can remove this ring and probably we would get a higher value for log D.